Yeah, I'm Chris Richardson. I actually have no affiliation with the Alan Turing Institute, but never mind. So I'm standing in today for Professor Garth Wells, and Garth can't be with us because he's on secondment to EPSRC at the moment. I'm not sure if I should say he's ascended to a higher plane or he's gone over to the dark side. But anyway, so these are actually his slides, not mine. So forgive me if I'm a bit incoherent or if I stumble here and there. I'll try and make some kind of sense of it. So many of you perhaps will be familiar with this beast, which is now getting a bit long in the tooth, Archer 2, which is our national HPC resource based in Edinburgh. And the one-line takeaway really from this talk is the project, the UKRI Living Benchmarks project, is that we're developing benchmarks that will influence future DRI investments. So if you get nothing else from this talk, that's basically the one-line takeaway. So, yeah, what is the background? Often when the government decides they're going to buy a new machine, it does it at short notice, and this is happening now. They've announced they're going to spend 750 million sometime in the next 6 months. Probably about half of that will actually be on hardware for a new machine, and the turnaround time is pretty short. And there's not really anywhere that's got the central expertise for how to run these procurements. And it's difficult to assemble a team with the skills at short notice. Also, the other thing is future systems will be including more diverse sets of users, obviously including AI, but also social sciences and different communities which are not necessarily represented at the moment. And not all procurements actually use benchmarking. So let's just have a look at how you go about procuring a new big machine. So more or less, you have it's a business transaction, right? So you're spending a lot of money, and there'll be a couple of there's usually one constraint, one major constraint, which is like how much money we've got, or it might be performance, often measured by LinPack, which is just flops, basically raw flops. And one will be a constraint, and one will be a competition point. So maybe you'll constrain the maximum price. Let's say it's going to be 400 million or something, and then you say, what's the best performance we can get for that price? Or maybe they'll say, we want this performance. How cheap can we get it? So that's normally how things go. Part of the problem, though, is there's not very much competition out there because there's only a few companies that actually make these really big HPC systems. So I suppose at the moment there's Cray HPE, and was it Atos, Bull, Sequana are the two big ones. And I guess there's other ones that might be out in competition like Dell, Microsoft, etc. But basically, there's not very many. And since pretty much all big machines these days are going to have GPU acceleration, we also have limited options for how that's going to be as well, because I think we can safely say that Intel are not really a big player anymore, so it's between AMD or NVIDIA for the GPU accelerator. And again, there's not much time, and that's a real problem for the vendors because they want to try and show that their machine is the best, but you've given them a limited amount of time to do that before you're actually going to spend the money. Right. So I mentioned already LinPack, raw flops that you can use to decide whether your machine is good or not, but actually it's not a very good benchmark. Very often you want the machine to do a specific job, or I mean, maybe a machine like Arch 2, it's a bit more general and it's going to have lots of different workloads on it, but some machines will be more focused perhaps towards AI or towards, I don't know, quantum computations or chemistry or whatever it happens to be. So you want to make sure that you have a set of benchmarks which is actually going to be something that measures the things that you're interested in. On the other hand, these are very high-performance machines. So you also want to make sure that the benchmarks that you choose are not just antiquated pieces of code that can't actually use the performance of the machine that you're trying to run it on. So an obvious example is that all new machines really are going to be GPU accelerated. So your benchmark code really must have some GPU part to it. Otherwise, it's not actually testing the performance of these machines. Right. So with all that in mind, this is the vision which was put forward for this project, the UKRI Living Benchmarks. We wanted to have a new sustainable approach to benchmarking. And what that means is that all the benchmarks, and there's going to be a suite of them, will be open source and publicly available. So anyone could just look at them at any time, especially vendors that can have a look and see how they work and what areas we're interested in. Some of them will be applications, so there'll be things like chemistry codes, let's say engineering codes, AI codes, social science codes, lots of different subject areas. Some of them will be synthetic, so they'll actually just be testing the raw performance of the machine, so checking the performance of the I/O systems, like file systems, or network, or let's say memory bandwidth. So those kind of synthetic benchmarks which really measure machine parameters. As I mentioned already, there should be a range of different domains across the sciences, but not just sciences, but all kind of research areas. And it should be led by people who actually understand the subject area and actually understand how to write high-performance software. So domain experts and RSEs. Also, it's not something, as the name suggests, it's living benchmarks. It's not something which is just going to be static once you just design it and that's it, it's finished. It's got to be something which is continuously updated. The software needs to stay up to date and use the latest compilers, and maybe also the suite can be refreshed. So sometimes there may be some code which say like this is no longer relevant. We want to bring a new one in. So it can be very dynamic. And hopefully this is going to give us deep understanding of what the performance characteristics of the machine or the machines that we can test are. So what this means is that when we come around to doing future procurements, and not just for national infrastructure, but for smaller machines as well, you can draw from a set of these public, well-developed benchmarks and choose the ones which are relevant for your purposes. And of course, the vendors themselves will be able to see them and hopefully provide some feedback and actually improve them too, so that get the best performance on their particular architectures. Okay, so how do we decide which things are important or valuable? I already mentioned they needed to be open source and sort of have high quality of software engineering, and not just the code itself, but also the whole infrastructure around it, the testing and the maintenance. But then we could say, should we be looking forward? Should we be looking forward to the new codes and things which are going to be future growth areas? Or should we be looking back and saying we've got legacy code or legacy areas which we need to continue to support? And I guess this is just a decision which can be made and doesn't really matter, but it's just a question which is out there, and in fact we have a suite of benchmarks. You can choose perhaps a selection between these different options. But what is important in terms of requirements is that they should be representative, that they're robust. In other words, that they can't just be the vendors, for example, cannot just make some change to the code which gets the right answer, but that basically defeats the purpose of it. So it just outputs the right answer, but without actually doing the correct computation or something like that. So you can't game it. Yeah, that they're scalable, that it actually works at small scale and large scale. So something which we'll be interested in doing both weak and strong scaling on these large systems. Should be easy to work with. So again, this comes back down to the software engineering of how you prepare code so that it's actually easy to install, often having correct package management systems. Yeah, is actively maintained, so it's not just been abandoned and got really old versions or difficult to compile. Obviously, it measures the right things. I already mentioned about how you want to make sure to actually use the hardware which you've got, and obviously having code which can do CPU and GPU is really important. So having said that, of course, the UK is not the only place where this needs to happen, and it has already been done in many other places. The UKRI have just inaugurated their Jupyter exascale system in Germany at Jülich, and they had 35 staff working for 18 months on benchmarking with 16 application benchmarks, 7 synthetic benchmarks, which were then whittled down to 12, which we used in procurement. So there's a paper, Andreas Herten came and gives a talk about this. And obviously that is the biggest machine that's actually currently running in Europe. Also in Italy, at Cineca, the Leonardo machine, 9 staff working for 18 months with 4 application and 2 synthetic benchmarks. So again, quite a big effort. So this slide, I think, is Garth has basically put this in because he was saying you might have different requirements for different machines and stretched. This is just a sort of illustrative. I think this is probably supposed to be like what school subjects you do, not so much about HPC. But the point being is that you might want to stretch your system in different directions depending on what your end use is. So whether it's, for example, you're procuring a system that's purely for doing genomics, it might be much more important to have high bandwidth I/O or large storage systems. Or, for example, you might be more focused on memory bandwidth or pure flops or whatever it happens to be. So you can choose the different stretch directions, and hopefully the benchmarks that we've got will be able to test the system in different ways, and then you can choose which ones are important for your particular requirements. And another point is that some benchmarks might, if you're not careful, exclude certain vendors. There are certain software packages which have been optimized so heavily for certain hardware that if you include them in your benchmark suite, some vendors will just simply say, okay, we cannot compete with that. It's not reasonable to, and they just will not bother to put in a bid. So you've got to be careful that you don't accidentally choose a benchmark which is so tailored to a specific hardware that it excludes people. Yeah, so as I already mentioned, Jupyter, the German or European system has got a benchmark suite, which has got a GitHub site. You can go and have a look at their benchmarks. Also, at Lawrence Livermore, there's a thing called Benchmark. So we're in touch with these people, to see what insights they can give us to help us with our project. There's also one which seems to be slightly abandoned from Prace, which has been there for a few years. So yeah, we're not just operating in a vacuum. It's a similar idea to have living benchmarks as other people have got. And another point really is that it's perfectly reasonable that these things are done in a national sense, because obviously most of the people who are using them will be based in that country. So Alice Lecoq, which is the second European exascale computer which is planned, is going to be using mainly French application codes for benchmarking. So it's perfectly reasonable that we're going to be doing benchmarking using UK-centered application codes. And it's only pretty right and proper. Okay, so another thing that's important to mention, and I already said it earlier, is that it's not just about doing our engineering code that we're interested in, but it's about reaching out across communities and making sure that everybody's represented. So whether that's the chemistry community or AI or social sciences or so many other different areas, and making sure that biology, that everybody who is there. And the important part about that is that it can help unlock funding, because UKRI are very much more favourable if you're including everybody. So I think that's an important point. Right, where are we at? Oh yes. Now this slide, Garth put this in, and I'm not totally sure exactly what's going on here. I did look up this earlier, but I think what he's trying to say is that it's perhaps stretching the title a little bit far. Living benchmarks. This thing on the left here is a product from a company called Cortica, who have made a computer which is actually based on real living cells. So it actually uses actual neurons. And this is a new kind of computing, I suppose, actually literally living. So I suppose the point of this is that technology is changing, and the idea of having a living suite of benchmarks is not that is that it can also adapt and change. So when the hardware changes, the software can also change. So new technologies come along, like I don't know whether this will will become something important, but for example, we already know quantum computing is very important, is a growth area. It will probably change the way that we think about particular algorithms, and we're going to have to adjust to take that into account. So it's not just about procurement, it's about having a set of software which can adapt to the hardware landscape. So we've got a website, ukribench.github.io. You can go and have a look and see what the current set of benchmarks are. You can actually suggest new ones or any comments at the GitHub site. And there is a bit of technical support and funding for benchmarks available. Yeah. So finally, a little bit about energy efficiency. This has become very important. This is the Frontier, which is one of the US exascale systems, and it uses about 25 megawatts. So I think it's AMD GPU based. Now compare that, so that's an exaflop machine, so about say 40 times more powerful than Arch 2, let's say. And yet the power consumption is only about 6 times what Arch 2 is. So we need to think a bit about our future procurements in terms of energy efficiency as well. Now, there's lots of things you can worry about with that. So where is your energy going to come from? Can you recycle the heat? So, for example, some big systems which have been built for Euro HPC in cold countries, that's quite nice because or near hydroelectrics or where there's cheap electricity, like in Finland or Iceland. But it still maybe have some issues. For example, the Euro HPC system in Finland overheated this summer because they had a hot summer. They weren't expecting that. So there's lots of things you can think about in your procurement, but this isn't really necessarily about benchmarking. And my personal opinion is that actually it's the other way around, that systems will become more energy efficient for other reasons in the procurement, and we don't actually need to worry too much about that in benchmarking because it will just naturally follow. So, for example, machines will use more GPU because it's more energy efficient, therefore benchmarking will have to be more dominated by GPU. So yeah, that's the question. Should it be directly assessed via benchmarks, or should it be the other way around? Is that the systems are becoming more energy efficient, and therefore the benchmarks have to follow? Okay, so I'm going to leave it there. This is the group of people who have been assembled for this project. So I'm on there, and Garth's on there, Mark is on there, a few other people. Not sure if anyone else is in the room, but obviously covering a diverse set of areas. And yeah, I think we've got a job ahead of us in the next few months because this is going to become more pressing with this procurement for the next national HPC. So thank you. Yeah.
Any questions? Yes, sir.
Thanks for a very interesting talk. I was wondering, instead of saying we are using software which comes from chemistry, physics, blah, 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 should we not say we are looking into memory intense software and we are choosing that particular software because it is in core, in memory only? This software is very intense in terms of message passing interface, MPI. This software is hammering your file system, and look from that angle, and then basically have synthetic benchmarks which are addressing these, what I just said, 3 different areas, for example. And so we are decoupling a little bit the development of software from our benchmarking, if you see what I mean.
Yeah, I mean, I think I did mention there are synthetic benchmarks in the suite as well. So we're not saying you shouldn't have those, but yeah, I mean, people talk about the seven dwarfs, the which are different aspects which you can use I can't remember what they all are, but they're different things that you can say that different softwares test. But I think it is really important to actually test application codes which actually are the real workloads that people are going to be using, because ultimately, yeah, you can do lots of synthetics, but it's when you put them all together to actually use for a real code. And I mean, the truth is that the majority of codes, for example, in Archer 2 are chemistry codes. I mean, that's just the way it is.
Any other questions? Viv, sure.
It's interesting that this is being done at this stage so NPL have curated a living database of the beginnings for benchmarking for quantum already, right? Much earlier stage. So it's quite interesting to see and compare those things. But more than that, there will be stuff feeding in for when you need to think about more diverse accelerators, hopefully. I mean, the standards they're still working on the standards even that would go with quantum, but those processes are active and will feed in.
Well, that's great to hear. I mean, I think one of the things that's important is it's obviously to have the codes there, but also to have as I mentioned, the infrastructure around them, so that you actually have something which is maintained and has good quality infrastructure and easy to install for people, because obviously with the time pressures for these procurements, it needs to be something that can be has kind of a standard install procedure. Basically, that's important. Yeah.
One last question. Okay, thank you very much.